Hello boys and girls. Well, in the next bit of our work on circular motion, there's one thing we haven't spoken about. And that's the fact that to keep something moving in a circle, you need a force to hold it in that circular path. So we're going to do a little bit of work that involves this rubber bung on a big bit of string and some masses. I've got a meter stick there as well. And the first thing I'm going to do is I'm going to make sure that this bit of string is 60 centimetres long to the centre of the mass. That bit of string is 60 centimetres long. Then it's going to go down through this tube, and then I'm going to put a mark on the end of it. Right, I put a little blue mark on the end of that tube, and that piece of string is 60 centimetres long, 0.6 metres. And what I'm going to do with this is I'm going to hold it. I'm going to hold this glass tube and I'm going to swirl this round my head. We're recording. Right, here it is. There's my bung. And I'm going to spin it, watch yourself. I'm going to spin it round my head. You can see that. Okay, now I'm having to hold on to this bottom end because if I let that go, then that bit of string would just shoot up the tube. There's a wee knot on the end there, stops that happening. Okay, so I have to hold on to it. And the reason I'm holding on to it is you need a force to keep this mass moving in a circle. Now instead of me holding on to it, I'm going to hang a mass on it. There's my masses, okay, 100 gram masses up to 1 kilogram, 10 100 gram masses. Right, I have hung a mass on the end of this piece of string. It's got this rubber bung at the end of it. And I'm going to swing it around my head. Remember, I put a wee mark on it, a little blue mark. And the reason for the little blue mark is so that I can see it. And that while I'm whirling that around my head, I can keep the blue mark at the same position. There it is. Now, if I go too slow, the weight of this makes it move down. If I go too fast, then this weight is lifted up. So, if I just want to keep it, with that blue mark in sight, there it is, right? Then this bung has to be moving in a circle at a certain angular velocity with a specific tangential speed. To keep anything moving in a circle, you need a force to keep it moving in a circle. We've met this before. Satellites orbit the Earth. They orbit the Earth because the force of gravity pulls it towards the Earth. It doesn't fall towards the Earth because it's got a horizontal tangential speed that keeps it falling around the Earth. Well, exactly the same thing is happening here. This rubber bung is moving in a circle with a constant radius, because I'm keeping an eye on that little blue mark. And the force that's providing that inwards pull to keep it moving in a circle is provided by the weight of this hanging mass here. So, I'm tired. Here's the point. If there's an unbalanced force acting on that rubber bung, then it must be accelerating. Which way is it accelerating? Towards the centre of the circle. And that acceleration is called the radial acceleration. Now, there's something a bit weird here. I've just said there's a force keeping this moving in a circle, an unbalanced force. An unbalanced force acting on this mass that's moving in a circle. Therefore it must be accelerating. It's got a radial acceleration towards the centre of the circle. But it's travelling at a steady speed. How can it be going at a steady speed and accelerating at the same time? Well, that's because velocity is a vector. Velocity's got two parts. It's got magnitude and it's got direction. And it's not the size of the velocity that's changing. It's going at constant speed. The speed is not changing. But what is changing is the direction. The direction of that vector is changing all the time. An acceleration, by definition, an acceleration is a change in velocity. And velocity is a vector. And because that direction is constantly changing, then the velocity is constantly changing. So what's the direction of the change in that velocity? It's towards the centre of the circle. Maybe need to think about that a wee bit. But just like a satellite that's orbiting the Earth, it's orbiting. It's got a constant tangential speed. At higher we said it's got a horizontal trajectory. But vertically it's accelerating down towards the centre of the Earth. Same thing happening here. It's got a constant speed, but it's accelerating towards the centre of the circle. Because that acceleration is along the radius, it's called the radial acceleration. Firstly, look, let's remind ourselves about Newton's first law, which states that an object will remain at rest or continue at a steady speed in a straight line unless acted upon by an unbalanced force. So if an object's moving in a circle, there must be an unbalanced force that is making it move in a circle. So by definition it must be accelerating. Newton's second law actually says that an unbalanced force will cause a mass to have a change in its motion. Now, a change in its motion, because velocity is a vector, that can either mean speed up or slow down or change direction. And in this case, for an object moving in a circle, it's the direction that's changing, not the magnitude of the velocity. So we have this big question. How can an object that's travelling at a steady speed be accelerating at the same time? Well, let's go back to satellite motion, where you did this at National 5, without the maths of it though. If a satellite's orbiting the Earth, it's got a constant speed around the Earth, but it's always accelerating towards the Earth. It falls around the Earth. The direction of that acceleration is towards the centre of the circle, along the radius of the circle. That's why it's called the radial acceleration. And it's measured in metres per second squared. It's a linear acceleration. So it's got a constant speed, but it's accelerating at right angles to that. Constantly accelerating towards the Earth. And that's true for any circular motion. There's a radial acceleration towards the centre of the circle. Now, there is an equation for radial acceleration. And there's two forms of it. You can either have it in the form where you have the tangential speed and the radius that the object is at, and that will give you the equation to work out the radial acceleration. Or you can get a form of the equation that's got the angular velocity and the radius of the object that's travelling in a circle. Either one of them, in fact, you should be able to show that this equation is an alternative form of this equation. Now, there is a derivation of this equation, and it's lovely, it's beautiful, but you do not need to know how to do it. It's not examinable, okay? But it's nice if you know your geometry, trigonometry, and a bit of vectors, you should be able to follow it. It's on the next two slides. I'm going to skip across it just now but it's there if you want to have a look at it. It's nice, and it leads to this. Anyway, there it is. There's a bit of maths going on in it, and it's nice, but I'm not going to waste any time on that just now. Let's have a wee look at this example though. Oh, same as me whirling something around my head. This is Katie Morag. She's whirling a little ball around her head at a radius of 0.8 metres. It's got an angular velocity of 4 radians per second. Remember, that's omega. What will you do? We'll calculate the tangential speed of the ball and calculate the radial acceleration of the ball and state what provides the force to produce this radial acceleration. Oh my goodness, big question. Let's have a look at it one at a time then. Is there any more? Oh, blimey, there is. Let's go back and look at it one at a time. The tangential speed of the ball, V, equals omega r. It'll just be 4 times 0.8, 3.2, if my mental arithmetic is correct, 3.2 metres per second. That means the speed of that ball, as it's going around the circle, 3.2 metres per second. What's the radial acceleration of the ball? Well, we've just worked out what the tangential speed is, and we also know what the angular velocity is, so you could use either form of the equation. You could use A equals omega squared times r, or V squared over r. Both will give you the same answer. Maybe worthwhile trying both. What provides the force to produce this radial acceleration? Well, that ball is connected to her hand with a string. There's a tension in the string that's providing the force that keeps the ball moving in a circle. If the tangential speed is doubled, what will the new radial acceleration be? You might be tempted to think, well, if the speed doubles, the acceleration will double. No, it doesn't, because the equation is A equals V squared over r. So if you double the tangential speed, then the radial acceleration will be 4 times as great as it was before. And why are these two equations equivalent? Well, remember that V equals omega r, so V squared will be omega squared r squared, and omega squared r squared over r is omega squared r. You might want to pause and jot that down. But those two equations are alternative forms of each other. There you go. Hopefully I got all that correct. Here's another example. The International Space Station orbits at a height of 400 kilometres above the Earth, and it orbits the Earth in just over 90 minutes, 92 minutes. Show that G at this height is 8.8 metres per second squared. That's acceleration due to gravity, which by the way is 9.8 at the Earth's surface, but it's slightly less than that at the height of the ISS. A lot of people think there's no gravity at the ISS. There is, it's just in free fall around the Earth. Anyway, what do? Well, we need some extra data here that the radius of the Earth is 6.4 times 10 to the 6 metres. Usually you would find that on a data sheet. So, if the ISS is at 400 kilometres above the Earth's surface, then the ISS is orbiting at a radius of 6.8 times 10 to the 6. I'm just adding 400 kilometres on to 6.4 times 10 to the 6. What do we need to do then? If we want to work out the radial acceleration, which is what G is, acceleration due to gravity is the radial acceleration, then we've got two forms of the equation we could use. We could either use V squared over R or omega squared R. Let's work out omega, the angular velocity of the ISS. Omega is the angle that it turns through in a certain time. Well, it turns through 1 revolution, which is 2 pi radians, in 92 minutes. 92 times 60. That gives us an angular velocity of 1.14 times 10 to minus 3 radians per second. let's just plug that into our radial acceleration equation. A equals omega squared r. There's our omega. Square it and times it by the radius that the International Space Station is at. And there's your answer. 8.8. Is that correct? Well, from a NASA website, G at the height of the ISS is 90% of that at the Earth's surface. Can we go to that and see it? Yep, there it's there. Earth's gravity is about 90% of what it is on the planet's surface. Okay. And 90% of 9.8 is 8.8. So, there you go. That's radial acceleration. Central force is for another day. Right, I skipped over the derivation of the radial acceleration equation because it's not examinable. And of course, some of you contacted me and said, can you go over the derivation of the radial acceleration equation? Because you are interested and you want to know it. So, yes, I should have. I am going to. Here it is. So, consider something is turning in a circle. Let's consider a point on this circle. And it is moving around in that circle with a constant tangential speed. So at one moment it is here, and it has got an instantaneous velocity in that direction. Okay? At some time later on, it will be here and it has an instantaneous velocity in that direction. But the magnitude of these two is the same. They are going at the same speed. Their direction is different. Now, what we said to you was that acceleration is the change in your velocity divided by the time, and velocity is a vector. So, this velocity is changing because its velocity vector is changing. It's v minus u over t. So if we want to work out the change in the velocity from this change in direction, then we have to do a vector diagram. Let me start here. And I'm going to draw. Now, it's v minus u. So there's our final vector. There is our starting vector. If I want to do v minus u, how do we add vectors? You draw the first one and then you add the second one. So, I'm going to draw v. Here it is. There's my vector v. Now it's v minus u. So if we want to add minus u, it would be a vector going in the opposite direction. So if u is going this way, minus u is going this way. So at the end of this first vector v, I'm going to draw minus u. Here it is. I think that's about it there. Okay. And there is my minus u. So that's v plus minus u. And the result of them going from start to finish is this vector. That is the change in velocity, that vector there. Now, I'm going to split it into two. Draw a wee dotted line down here. Because that is the change in velocity, so that's the change in velocity over 2. And that is the change in velocity over 2. That plus that equals delta v. The reason for splitting it is because if we just look at one of these triangles, now what I should have done was I should have said, if this point on the circle rotates from here to here and it rotates through an angle theta and then through another angle theta, okay, so that angle there is 2 theta. That angle there will be theta and that angle there will be theta. Now, the reason for that is, let's go and do some old-fashioned Z angles from school. So, let's see. If that's theta and that's a Z angle, that must be theta. So that must be 90 minus theta. And if that's a right angle, Then if that's theta, that's 90 minus theta, that's 90, that must be theta. So because that is theta, that is theta. Same there, if that's theta, this is theta. You might want to pause that, have a wee think about that. Anyway, next step. If this is theta, then the sine of that angle, sine theta, is the opposite over the hypotenuse. That's delta V over 2 over V, okay, which is delta V over 2V. If we rearrange that, because sine theta equals delta V over 2V, then delta V equals 2V sine theta. There we have an expression for the top line of our acceleration equation. Acceleration equals delta V over t. Delta V from our vector diagram is equal to this, 2V sine theta. That takes care of the change in velocity. What about the time? What about the time that it takes for this point to get from here to here? Well, it's covering an arc of the circle, the arc AB, and it will do that at whatever this constant speed is. So time equals, well, time just equals distance over speed. It's the distance or displacement, if you like, around the circle divided by the speed that it's travelling at. Well, that's the arc AB divided by whatever the magnitude of the velocity is. Now, arc AB, because S, remember S equals theta r, it's the angle that you turn through times the radius. So, the angle that we're turning through is 2 theta. It's 2 theta r over V. Now let's put it all together. If A equals the change in velocity over the time, there's our expression for the change in velocity. That's 2V sine theta over the time, which we've got here, 2 theta r over V. We've got a double division here. What happens if you get double division? V divided by V is V squared. So that gives us 2V squared sine theta over 2 theta r. 2's cancel out. I'm going to go down a line. No, I think I've got room here. I'm going to rearrange this a wee bit and say V squared over r times sine theta over theta. Now, let's talk about this for a wee second. There is a statement that you will sometimes see quite often. It's this: for small angles, sine theta equals theta. Now, what that means is, and if I show you this on a calculator, make sure, by the way, that your calculator is in radians. If it's not, press shift, mode, and it's number 4 for radians. So I'm in radians. If your calculator's in radians and you do the sine of a small angle, remember 1 radian is about the size of that angle between my finger and my thumb. So that's quite a big angle. So a small angle is about maybe 0.2 of a radian. If I do sine 0.2, then the answer is 0.2. Sine of 0.2 is 0.2. Or smaller than that, the sine of 0.1, sine 0.1 is 0.1. So, for small angles, it's called the small angle approximation. Sine if your calculator's in radians and your angles are in radians, then sine theta equals theta, which means if we go back over to here, if that is approximately equal to that, they cancel out, and we are left with A equals V squared over R. And that is the radial acceleration equation. Now, as I said, there is a second form of it. There's A equals omega squared R. How do we get that form? Well, that's from the earlier equation we met, that V, the tangential speed, is your angular velocity times the radius. So V squared is equal to omega squared R squared. If we substitute that in there, we end up with A equals omega squared R squared over R. Cancel out one of the R's, and you end up with omega squared R, which is that equation. So that's the whole lot. Remember, it's not examinable, but I think it's beautiful. It shows you that the instantaneous, when these vectors are very, 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 very close together, then the instantaneous change in velocity over a very, very, very short period of time mathematically leads us to this equation. That is the radial acceleration. Sometimes you might see a wee r as a subscript there. And radial acceleration is measured in meters per second squared. It's the acceleration directed towards the centre of the circle. Hope that helps.